So when we talk about functions, there are two things that I mentioned previously. You might have learned about domain and range in your previous years in metrics or in STPM, but I prefer to see it in the form of logic. Yes, I know some of you might have read about calculus, but functions, there are three ways to represent functions. First, we have what we call as graphical illustration, and then we have algebraic representation, and also we have logic. Okay, logic ways to view how function works means that you consider several inputs, okay, plug in into the machine, and then the machine or the logic process the input and then produce an output. Like you have f x, right? F and then we have x in the bracket. You know that x is the input and then fx is the output. Or maybe you can have two input fxy and then you have different output z for function of two variables. So as you can see, I accidentally found this thesis on sugar babies. I know that this is quite an issue previously. Okay, a couple of months ago about sugar babies trend in Malaysia, but students seeking for sugar daddies. I'm not sure whether that happened in USM or not. Okay, sugar daddy, sugar babies. I believe a lot of you understand the meaning. If you don't understand, please ask your friends. So, student sugar babies. This is on seekingarrangement.com in Canada. So the way we see function here, okay, like I said just now, we have input output. Okay, so the input that we have here, okay, the input that we have here is the year, and then the output that we have there is the number of student sugar babies. Okay, this one not in Malaysia lah. This one is in Canada. So you can see that in 2012 they have uh, 82,000 student sugar babies registered on their platform, and then the number keep increasing every year until 2016. Some of us might see this as a very bad things, but from a different perspective, we see that there are struggles among students. Okay, there are some, uh, you know, explicit reason why they involve in these sugar babies, sugar daddies, and that has been studied a lot by researchers. But we see that the trends are increasing, okay, every year. But and I believe in 2021, with all these COVID things, okay, the number will keep increasing. But you know that when you learn about calculus, you know that how to check whether a function is increasing and decreasing from the graphical illustration. Okay, you can see that the trend is going up. But later on, when we are going further deep into functions, we see that there is a way to determine whether our function is increasing or decreasing. You select 2 points on your domain and then you check their output or their range. For example, in this case, you want to compare. You want to check whether our functions here is increasing or decreasing. Then you check two points in our domain. For example, we have 2012 and 2013, and then you check the value 82,000 and 114,000, and you see that F 2013 is bigger than F 2012. That we will see later on. This one is of course very easy function, but later on when we are doing exercise and so on, you will see a more complicated function that cannot be illustrated by using graphs, but you have to be able to define whether it is increasing or decreasing, okay, algebraically using calculation. And I believe a lot of you are from School of Biology. So let me share with you. Okay. So since a lot of you are from biology school, I believe you have heard about prey-predator model. And one of the famous one is of course Lotka-Volterra predator-prey model. So you can see in this here. So researchers in the past have tried to use functions, okay, to determine the patterns of increasing or decreasing of prey and predator. As you can see in this figure here, the blue lines represent the predator, and then the uh, yellow one here represent the prey. So you can see when the number of prey is very high, for example, you can see at the peak here, okay, the first peak here, the number of predator is very low. And then because of that effect, okay, because the number of prey, the number of food is increasing, the quantity of food is increasing, then the number of predator increase again. And when the number of predator is at its peak here, the blue peak here, then you see that the number of prey is less. And then you can see the oscillation between the number of prey and predators. Okay, this has been modeled from real life applications that I believe some of you biologists will be, maybe you will do model in biology, maybe something related to growth, population growth, or bacteria growth. Okay, you will be using a lot of functions to represent them. Maybe not at this undergraduate level, maybe after you go to into the industry, okay, you get a job and you try to do something with your biology, you have to be able to understand the function, not everything, but at least a little bit that can be used to explain the phenomenon that you have in your population, for example. Okay, let's go back to our, okay, the topic of sugar daddy has been, okay, speak a lot in the chat box, but it's okay. No worries. I will go back to my slides. Okay, wait, I need to be able to comment my slide first. Okay, so that I can jot down on the slide. Okay, change to right. So this is the topic that we are going to discuss today, even though it is, considered as one of the contents of this course, but I think at this years, okay, 2021, 2020, 2020, 2019, you have learned about this. Functions has been, plugged in into the syllabus in Form 5. And even if you go to MRSM, for example, functions have been taught to Form 4 students, for example. And of course, in STPM and as matriculation, you have learned about functions. So we will go through and try to see whether the understanding that we have acquired all the years, okay, can still be related to what we have here, and maybe we try to relate it to some of the application. So functions and their graphs. So when we talk about functions, of course, the first thing that you need to know is domain and range, and you have learned about this. Like I said just now, there are three ways to represent, okay, to talk about functions. First is, of course, graphically. And second, we have algebraically. And the latest one we have using logic. So what we have here is, of course, using the concept of logic, where you have an input, okay, you plug in into your machine, maybe your brain, and then you have an output. You can imagine this. You are the machine. You look at something, and then you produce your thoughts or your perspective that can be considered as an output. But of course, when we are considering function, most of the time we are going to consider continuous function, and we are going to see that later on, later in details. So graph is actually, the concept of graph algebraically have been discussed a lot by Newton and Leibniz. Okay, we don't know who was the first one to invent calculus. If you try to read it on Google, some will say Newton, some will say Leibniz, but ijma, or most of the mathematician, okay, jumhur mathematician, agreed that they both founded calculus on their own, separately, even though they are living in the same years. They were living in the same years, okay? And then come the new processing type, okay, using computer sciences. Of course, a lot of computer sciences use logic. And then we have another representation of logic. But these two has been, okay, uh, discussed a lot since the year of Newton and Leibniz. Okay, jumhur ulama matematik. Jumhur mathematician, I would say. Okay, so this is one example of diagram, okay, to say that a function f from a set d to a set y, okay, we say x is in d to a set y, so fx is in y. So this is the notation that I use for in, or element of fx is an element of y. So uh, from a function f from a set d to a set y, set d to a set y is a rule that assigns a unique value fx in y to each x and d. And you might have heard a lot of functions. You have linear functions, you have quadratic functions, But if you are seeing this as logic, it can be any functions. The function can be your brain, or the function can be any sensor that can take an input and produce an output. So this is a diagram illustrating how uh, the logic functions in the form of machine. Okay. So this is another representation of domain and range. So D again is domain, Y is the set containing the range, or you can say the output, domain is the input. So this is illustration. Let's say you have a set of numbers. Okay, you can imagine this as a bucket. For example, this is another bucket. Okay, let's say you have a number of balls here. So you can see that this uh, pink color, okay, pink circle here as balls. Okay, so for every balls that we have in this bucket D, okay, can be mapped to another number, another ball, the blue balls inside the bucket Y. Okay, can imagine it. Okay, you take one and then you plug into one. You take one and you plug into another one. Okay, but you have to know that there are certain rules. Okay, every single point that we have here, the rules that every element of the domain must point to something in the codomain. Okay, or the range. Let me write down. You can also call the range as codomain. And no element can point to more than one thing. Okay, so it means that for single points here, you cannot have it to point at two different balls. So one single point here must point to single balls here. But two different points in bucket D can point to a single point in bucket Y. Okay, this is just an illustration. Move to the next slide. Okay, so again, you have to know about the interval notation. We have reviewed this in pre-calculus lecture. But of course, you can review this on your own. Okay, we have more. If previously we have like 4 or 5 only our discussion, but now we have 1, 2, 3, 4 until 8 type of interval notations. But I think you understand. Means that when you are using this kind of notation, means that you are including the boundary A. Similarly with B here. And if you are using this kind, okay, you don't include B in your interval, you have to use this kind of notation. Okay, but it's the same everywhere. Okay, so why do we use this open bracket when considering negative infinity or infinity? It's because infinity is not a number. Okay, you can always go bigger and bigger than a number that you choose. For example, I say that infinity is 1 million. I can always find a number that is bigger than 1 million. I can say 1 zillion, but there is always number bigger than that. That's why we have to use this uh, open notation. Okay, this is open. Okay, this one is what we call as close. So okay, this one you can review on your own after this. So now let's try to practice. Okay, whether you still remember what is domain and range. So I'm just going to be quick on this slide. So of course, the first one, we know that it can be any real number except 0. So x here cannot be 0 because you cannot divide by 0, right? So you have real number, remove 0. Okay, you can use different notation lah, of course. Okay, you can use x less than 0 and x greater than 0. No problem. I accept all or any type of notation. Maybe you read different books, you use different notation. But I prefer to use this one. I can use real number, remove 0. And of course, the domain will be the same as well. Real number, remove 0. Okay, I think you have no problem lah because you are not dividing. Okay, you have 1 at the numerator, so you will never get 0 as your output. The second one here, we have y equal to square root of x. You know the concept of square root, right? When you have square root, the number inside the square root, the argument of the square root cannot be less than 0. So x greater than or equal to 0. It can be 0, but it cannot be less than 0. Because if it less than 0, of course, we do have tools to handle that kind of numbers, less square root of less than 0, but that involve imaginary number. But in this syllabus, we are going to focus on real number only. But if you are interested in complex number, feel free to explore it on your own after this. And of course, we also have the same domain. Okay, y is greater than or equal to 0. Okay, so the second one, you still have the same thing here. The argument inside the square root cannot be 0. So 4, cannot be less than 0. So 4 minus x must be greater than or equal to 0. Or you can do some manipulation and then you'll get x is less than or equal to 4. And then here, you still have the same number, greater than 0. Okay, so you understand, huh? Because if you plug in number greater than 4, for example, you plug in 5, you will have x equal to 5, then 4 minus 5 will give you negative number, which is negative 1. So you cannot have square root of negative 1. That will give you imaginary number. And then we have 1 minus x squared. Last one, maybe a bit tricky for you. You know, okay, the first fact is 1 minus x squared is greater than or equal to 0. Wait. Okay, so you need to do some factorization, okay, to check the value. Still remember, you have a square minus b square. So you have a minus b, a plus b. Okay, let me do it to find the critical number first. We have this equal to 0. We want to find the critical point, the maximum or the minimum point. So from this one, you'll get x equal to 1. And from the second factor, we have x equal to negative 1. So I prefer to draw a number line. Okay, so you can label. This one is negative 1. This one is 1. And then you try to plug in values that is within this interval. And then within this interval and also in this interval. Maybe you can try to plug in 0 here. Okay. So what will happen if you plug in 0? You will get it greater than 0. So of course, 1 minus 0 is greater than or equal to 0. So you can accept this interval. Okay. And then you can try to plug in here. Maybe you can try to plug in 2. And then you have 1 minus 4, which is less than 0. So you cannot accept the interval. Similarly here, you can try negative 2 and then you'll get the same value. So finally, you can conclude that your interval is actually, okay, within negative 1 and 1. Okay, so or you can write it down like this one. Okay, so it's the same thing. I know a lot of you prefer to use this one. It's okay. You don't have any problem. If you prefer this one, also no problem. Okay, so the range here, of course, is the same as what we have previously. Okay, but with a little trick, of course, must be greater than 0. But what is the maximum value that it can have? Okay, you can try to plug in. This is a x squared is always a positive value, right? So if you 1 minus negative 1 square, you get 1 plus 1. 1 minus 1, I'm sorry, is 0. And then this one is 0. But the maximum will be when x equal to 0. So 1 minus 0 will give you 1. So square root of 1 is 1 itself. So it lies between this. So 0, okay, y is between 0 and 1. You can see you cannot get any value bigger than 1. If you plug in any value, okay, that is outside this interval, okay, you will not get a valid one first. But then you have to consider the one that is inside this interval. Of course, you have to check the boundary here. So when you plug in the value at the boundary, negative 1 and 1 at the place of x here, you will get 0, right? 1 minus 1. Okay, you get 0. 1 minus negative 1 square and 1 minus 1 square, you get 0. But the maximum, okay, you will see this in details later on when we are discussing about extremum functions. But now in general, you see that the maximum happen when x equal to 0. That will give you y equal to 1. That's why we are considering this one. Okay. Let's move to the next slide. Okay, so there are several types of functions that you need to know. You have seen this a lot previously. Because we have a linear function, okay, that comes from the word line. So it is a straight line. Okay. So it's straight line, you have y equal to x plus 2, for example. Or in general, you have it in the form of y equal to mx plus c, where m is the slope and c is the y-intercept. Okay. Or you can try to use any form that we have discussed in the previous lecture. This is just to recap what you have learned. So of course, apart from linear, we have non-linear. You might have deal with quadratic, maybe, I don't know. Maybe you have deal with cubic. Maybe some of you might have learned or explored a little bit on quintic. Okay. And then we have, we have quartic first. Quartic is power of 4. And then we have quintic power of 5. Okay. Quadratic power of 2, power of 3, 2, 3, 4, 5, and so on. And apart from this, we also have transcendental functions like the trigonometric functions. Okay, you still remember tangent, sine, cosine, those are non-linear, something that cannot be represented by a straight line. So we have non-linear function. So this is one example. Okay, you don't have any strict ratio between your x and your y, like we have mx plus c. So it can be any values. So you can have a very weird graph. For example, you can have, okay, no problem. As long as it is still defined as function. This one, of course, not, because we have two values for single value of x. You need to be a little bit curved there. So it says here, if xy lies on the graph of f, then the value y equal to fx is the height of the graph above the point x. The same with linear function. We also have the concept of height here. It's the same thing. And of course, okay, we can try to represent the function in the form of tables. Okay, when you have function given by y equal to x squared, that you can graph like this one. Okay, but in order to be able to graph this, okay, using no tools, okay, you don't have any tools, you don't have any skills of second derivative test, first derivative test. The only thing that you can do is, okay, non-linear graph be testing your drawing skill. No worries. We are not going to consider that. I will allow you to use any function unless I say you have to sketch the graph, then you sketch the graph. But if I say plot, you can use any software, any available online software. So here we have the function given by y equal to x squared, and then we want to try to plot the function. Of course, we need to find the points. Skills that don't exist. Okay, no worries. We will try to polish that. So we have here 4. Okay, you can try to answer this on your own. And then we have -1 square, give you 1, 0, will give you 0. Then we have 1, and then we have 9 over 4. Okay, 3 square and 2 square will give you 9 and 4. And then you have 2 square, which is 4. Then you can plug in the values here. Okay, I don't have much space here. Okay. One. So using your flexible ruler from the point that we have here, you have to plot your graph as smooth as possible. Okay, using your hands, why not? Okay, so this is one example of how functions, okay, we obtain a series of data, numbers of data, okay. This is from experimental, I believe. So these are musical notes, okay. So we measure the pressure waves in the air. And then we want to see. So this is experimental. You can imagine in the first place, they don't have the cosine, the tangent, the sine function. So they have the time. Okay, maybe you have some sort of machine because the time is very close to each other. And then we have the pressure measured at that particular time. Okay, so you can see at this time, what is the pressure? Okay, so the data given recorded pressure, displacement versus time. Okay, in seconds of a musical note produced by a tuning fork. Okay, you might not see any patterns when you are looking at this table. See why it's just suddenly increasing and then suddenly decreasing again and then go to negative values. But if you try to plot every single points that we have here, you have this kind of function. Might not look very nicely. Maybe when you are doing this experimental, not the researcher, maybe you can have some point here, some point here. But this is just some simple errors that we can normally see when you are conducting experiment. So you have this kind of plots, okay, the blue one that we have here, and then using your smooth ruler, the flexible ruler, you plot this function. But of course, when mathematician is doing this kind of uh, experiment, they can see that, oh, this function or this data do portray some sort of function. Maybe it look like a sine, maybe it look like a cosine, maybe it look like a cosine that has been shifted upwards, shifted downwards. Maybe it's not the one that you are very familiar with, amplitude one, and then you have one at the top, one at the bottom. Maybe this one is the cosine function that has been compressed. Okay, which we will look later on when you are discussing about transformation of function using shifting, compressing, and so on. So this is something, maybe it's not really a miracle right now, but you think in the past when we don't have any information about the type of function that the waves represent, suddenly we get this kind of smooth functions. Must be very, well, the scientists at that time might be, oh, Eureka, we have something very good here. Okay, maybe that's what happened. I don't know. It's just my drama. Okay. So next we have how to determine if the graph is a given function or not. So of course, the simplest one is by using the vertical line test for a function. So, okay, technically we have an equation specifies a function if each vertical line in the coordinate system passes through at most one point on the graph of the equation. Okay, so the keywords that we have here is vertical line and at most 1 point. So it cannot cross or cannot passes through 2 points. For example, this one, if you have this kind of function, you might be familiar with circle, right? X squared plus y squared equal to 1. So this is a unit circle. Means that you have radius equal to 1. But this certainly is not a function. Okay, from our vertical line test, we draw a vertical line and we see that the line passes through 2 points on our circle. Means that this equation is not a function. But you can actually redraw it, okay, focusing only on the top part and the bottom part separately. So here we have for the top part, and then you can try to use your vertical line test. You can draw anywhere that you want, okay. Actually, you have to draw everywhere. But yes, from by looking at it, we know that whenever or wherever you draw your vertical line, you will only pass the graph once. So it's the same thing here. So only pass the graph one. It means that this is a function and this is also a function. Okay, so this is the software, the graphing calculator. Okay, we use graphing calculator to draw and then we try to draw the vertical line test. And then we see, okay, whether it is a function or not. So it's just, maybe some of you have extra money and you want to buy graphing calculator, it's very good for you. But you can always opt for online graphical software like I shared with you in the previous lecture. In the e-learning, I use Desmos graphing software. It's quite sophisticated and quite beautiful and easy to use. And then we also have piecewise defined function. It means that your function, okay, not only defined by a single equation, but it can be defined by several equations. Okay, this is one example, but maybe in the future you can see this kind of form. Okay, maybe the first one you have x plus 1, and then you have x plus 2, and then maybe the third one you have x squared plus 1 for a given interval. This is just one example. Okay. Okay. So it's not strictly mentioned about the absolute value. Could be anything. Okay. So you should get used to it. So this is one example of a very trivial piecewise defined function, the absolute value function, means that it can exhibit two values, x and negative x. So I asked some of the students in my previous class, and they're not sure about absolute value function here. Will it be negative here? My answer is no, because we are dealing with the interval itself. The number here, in the first place, for the second equation here, negative x here, this number here is negative. That's why we take another negative, because double negative will make a positive. But two wrongs don't make a right. Okay. So you understand this one? So okay, you can try to draw it on your own. Of course, domain and range is very simple. You can take it directly. Okay. So maybe you can try to plot this one. Okay. First, we see the interval. Okay. Below, less than 0. And then we have greater than or equal to 0. But actually, it's the same value here when x equal to 0. Okay, because x is equal to 0, so you can consider this one, and consider this one. So sometimes you might see that it is like this one, x greater than 0, but it will give you the same value because of the concept of limit that we learn in the next chapter. So you can try to plot this on your own. Okay, so it is a straight line here, and then it's a straight line here. But this is a very trivial one. Normally, we will consider this kind of piecewise defined function. It's not restricted to any values. Could be any function. For example, this one. We have fx is x can be portrayed by three different functions according to their intervals. So first one, for x less than 0, we have fx equal to negative x. And then we have between 0 and 1, which is x squared. And then we have fx equal to 1. It's a constant function when x greater than 1. Okay. So, okay, it's simple here. We have, I don't want to be the lecturer that having the hard time to explain the piecewise functions, of course. So, of course, the first thing that I want to consider is x less than 0. So we have negative x. So we have negative 1. Then we have negative 1. That is 1. And then we have negative 2. That is 2. So I'm doing this one first. So we have two lines here. Okay, let me just put the dots first. And then second one, we have a quadratic function. Okay, the only point that we have here may be here. Okay, from the domain. Okay, you can have 0.5 here. So it will be 0.25, right? Between 0 and 1, 0 and 1. So 0 and 1 here. So from 0 and 1 here, we have quadratic function. And of course, you still remember your smiley and your sad face. Okay, so this is, of course, the smile face, but only a portion. Then we have x greater than 1. So this interval here, which is given by a constant function, 1. So 1, 1. And then for 2, we also have 1 because it is a constant. So after that, just use your flexible ruler or your hand. So first we have this one, sort of straight line. And then we have a quadratic function. Okay. So of course, if you are considering the smiley face, okay, the tip here is 0, 0. So we need this small interval here from 0 to 1, which I'm not good at drawing this, of course. But I think it look like something like this one lah. Yeah, it should be this one. Okay. Okay, the curve quadratic. And then we have the constant function. Okay, can which go on forever because we can also replace that with 1 until infinity. So it can goes on forever. So same here, can goes on forever. Okay. A very, very simple one. Later on, we will see the concept of limit that can be used to join between this function. Okay, this is piecewise defined function, another familiar one. Okay, so we have here integer floor function. So don't worry about integer. Integer means whole number. Okay, I know some of you might have trouble when trying to remember the definition or the notions that is used in maths, but no worries, integer is just whole number. And floor is of course meaning something that you step on, the bottom one. So 2.4 will give you 2, 2. Then 1.9, the bottom one is 1. 0.2, this gives you 0. 0 will give you 0 because it is a whole number itself. Then negative 0.3. What do you think will be the value? Okay, can you answer in the chat what will be the answer for this one? Okay, we have one answer 0. Okay. Remember, it must be lower than the number itself. Let me draw you a number line. This is 0. This is negative 1. This is 1. Yeah, it's negative 1. Because we have negative 0.3. You have to choose a lower value, negative 1. So you have here negative 1. And then this one you have negative 2. And then of course this one is a whole number. We have negative 2. Good. I don't think you don't. I'm not saying that you don't know, but negative 0.3 here means that you are a bit careless. So you have to be careful next time. Okay, because you are seeing the flow of what we have previously with the positive number, and then we transform or we do a transition from positive number to negative number, and then you still follow the same trend, then it's not good. You have to see the you know the what you say the motion or the direction of positive and negative numbers. Next, I think I don't have to explain more. Okay, we have least integer function or ceiling function. Ceiling is something on top, so just on top. So I don't need very much details on the examples here, but I think you can understand. Okay, you can see from the figures here. Okay, for any value between 2 and 3, for example, maybe you have here 2.5. Okay, it will give you a ceiling function. So ceiling of 2.5 is equal to 3. That's why we have this equal to 3 here. So it's the same everywhere else. Okay. So similarly, if you have, for example, negative 1.4, okay, sorry, negative 1.4, the ceiling of negative 1.4. So negative 1.4 will be somewhere around here, okay. Okay. So it will be negative 1, of course. The ceiling is equal to negative 1 because negative 1 is bigger than negative 1.4. Okay, that's why it's here negative 1. See? So don't get confused. The name itself already represent what it meant. Ceiling and floor. So now we have increasing and decreasing function. Okay, maybe we want to stop here. And I guess that's it for the class today and the task for attendance. Okay, before that, any question? Okay, the next class we will continue from here. If not, I will share the task lah. Okay, while I'm sharing the task, if you have any question, you can put it in the chat box or you can message me later or email me, of course.